Hello students, I welcome you all on this YouTube channel. You are most welcome. So, in the earlier lecture, we have discussed that why brush shift is required due to the change in load. Let me give you a quick recap. So, brush shifting is required due to change in load. Due to change in load, brush shift is required. Why? Because we want to avoid sparking, right? If you place your brushes at origin position and if the load is changed now, then this particular coil which is nearby this brush, at the time of commutation it will definitely give sparking when it will be shorted by this brush bit, right? Because this coil, it is having the rotational voltage. So at the time of short circuiting by brush bit, it will give sparking definitely, right? So if you shift these brushes, then you can avoid this sparking, because at this position when brush will be shifted, then coil after rotation, when it will come at this and this position, then at this and this position, this particular coil, it will be having zero rotational voltage, right? At this position and at this position, the coil, the armature conductor, it will be having zero rotational voltage, and that's why at the time of short circuit by this brush bit B1 and B2, it will definitely not give sparking, right? And this is only possible if you shift these brushes to new magnetically neutral axis. That means MNA at load, it will be this one, right? This is a new magnetically neutral axis on which you have to place your brushes, right? So basically brush axis is basically MNA, right? So every time for the new, when the load changes, every time magnetically neutral axis will shift, and every time you will have to shift your brushes to avoid the sparking. So since that's a problem, every time when the load changes, you are bound to shift these brushes to avoid sparking. So that's why this method of brush shifting is only limited to small DC machine, and this method of brush shifting is not advisable for large rating DC machines, right? So this much we have already discussed in the earlier lecture. So this was a quick recap, right? So let me go further. Now in this lecture we will further discuss the calculation of demagnetizing armature ampere turns, right? Calculation of demagnetizing armature ampere turns. So here, see, this is the two-pole DC machines. For simplicity, I am assuming a two-pole DC machine for the explanation, for simplest possible explanation. I am using two-pole DC machine. So this north and south, they are representing the main field poles, right? Okay. So now our aim is to calculate the demagnetizing armature ampere turns, right? I have already explained the reason of reduction of main field flux per pole. See, why main field flux get reduced? See, it is due to the effect of armature reaction. See, I have already explained this in the armature reaction lecture. See, due to this phi ER demagnetizing, which is directly opposing this main field flux phi EF, it is reducing this main field flux, and this is undesirable, definitely undesirable. Why? Because if the main field flux, if it will collapse, if it will reduce by this phi ER demagnetizing component, then definitely the generated EMF in case of generator will reduce, right? And if the generated EMF in the generator reduces, then definitely the terminal voltage of the generator will collapse, it will decrease, and this is certainly not desired. It is definitely not desired, right? Because at the terminal of the generator, what you want a rated voltage, always you want a fixed voltage, right? But it is getting decreased by the effect of this armature reaction. if we will not tackle this armature reaction, if we will not take adequate measures to nullify this effect of armature reaction, then the terminal voltage in case of generator will definitely fall. Why it will fall? It will fall because of reduction of this net main field flux, right? Why this main field flux is reducing? Because of this phi air demagnetizing. What is this phi air demagnetizing? This phi air demagnetizing is the demagnetizing component of armature flux, armature reaction flux, right? So I told you that when the crowding of main field lines will take place at the trailing pole tips of this generator, right, then the resultant flux, it will come somewhere here, and that's why due to this the magnetically neutral axis will shift, and now this phi air will come at this position, and now it will be resolved. It can be resolved into two positions. One component will be resolved in the direction of vertical direction, and another component will be resolved in the horizontal direction. So this vertical component of this armature reaction flux is known as phi air demagnetizing. Why it is called demagnetizing? Because it is directly opposing this field flux. And the second component, which is in the direction of horizontal direction, it is called cross magnetizing. Why cross magnetizing? Because it is crossing this vertical axis. That's why cross magnetizing. But the component which is responsible, but the only component which is responsible for this reduction of this main field flux is this demagnetizing component of this armature reaction, and not this cross magnetizing, right? Keep in mind, right? So our aim is to calculate this demagnetizing armature ampere turns. That means we want to now calculate the demagnetizing armature MMF. So have a look at it. So this was a quick recap that I given to you from the armature reaction lecture. So how to calculate this demagnetizing armature ampere turns? See here. So first of all you have to find out which armature conductor are responsible for this demagnetization of this main field flux. Which conductors are responsible? See here. So when you shift these brushes to avoid sparking, then you can find out this demagnetization armature ampere turns. Ampere turn means MMF basically, right? So suppose your brushes are shifted by an angle beta electrical, right? Suppose your brushes are shifted by an angle beta electrical, right? So beta electrical is that angle by which you are shifting the brushes. That means from this horizontal axis, if you are shifting your brush to the new magnetically neutral axis, see, this is the new MNA, right? This is new magnetically neutral axis at load. I have already explained this. When the load will change, magnetically neutral axis will also change, will also shift, right? And accordingly you will have to shift your brushes. You're bound to shift your brushes, otherwise the sparking will occur for sure, right? If you will not shift your brushes, then sparking will occur. I have already explained this, right? So now when you shift your brush for the new magnetically neutral axis, that is this line, this one, right? Then your aim is to calculate the demagnetization armature ampere turns, right? So our aim is to first find out which armature conductor are responsible for demagnetization action, right? So for all those armature conductors, it is clear from this above figure that only those armature conductors which lie in this 4 beta electrical region. See here. Why I am saying 4 beta electrical? You have shifted the brushes by this angle beta electrical. So this angle, this particular angle, this angle is beta electrical by which you have shifted your brushes, right? So this brush B1, which was at this position earlier, you have now shifted it at this new position, right? So this is the new position of this brush. That means you have shifted this brush by beta electrical angle, right? So that means if this is beta electrical, this is also beta electrical by symmetry, by geometry, right? So this is also beta electrical. You understand? So this total angle, this one, from here to here, this angle, this total angle become beta electrical plus beta electrical. This particular angle, this angle become 2 beta electrical. So by symmetry, this angle will also become 2 beta electrical, right? So let me write 2 beta electrical, right? You understand now? So that means over entire periphery of this armature, or you can say rotor, 2 beta electrical here and 2 beta electrical here, right? So total 4 beta electrical armature conductors will be responsible for demagnetizing armature MMF, for demagnetization of main field flux, right? See here, why I am saying this, because why it is demagnetizing? Because in this region the armature coils will be having this cross polarity, and here in this region the armature coil will be having this dot polarity. Are you getting this? Here it is cross, here it is dot. So when you apply right hand thumb rule like this, right, then where my thumb is coming? My thumb is coming like this, upward. Just apply right hand thumb rule. Cross means it is your finger should go away from you like this, right? And here it is dot, that means your finger should curl and should come towards you like this, right? So from here current is entering like this, and from here current is coming, exiting like this, right? So when you apply Fleming right hand rule like this, then your thumb is coming upward. That means this is the upward, means this is the demagnetizing component of armature reaction. Remember that original figure which I have already given to you, this one, right? So this component phi AR demagnetizing, this particular component is responsible, phi AR demagnetizing is responsible for the reduction of this main field flux, right? So this is called demagnetizing because it is directly opposing field flux, right? So now we will calculate what are the armature conductor which are responsible for this demagnetization action. So we have calculated that for all the armature conductor which will lie in 4 beta electrical region, that means this region and this region, this region and this region, this region and this region. So for all those armature coils or armature conductor which lie in this region, that means 2 beta electrical plus 2 beta electrical, 4 beta electrical, for all those conductor which lie in 4 beta electrical region, only they will be responsible for demagnetization action of armature reaction, right? So 4 beta electrical over 360 degree armature periphery. Remember, 4 beta electrical is for 360 degree periphery, right? You have taken whole periphery. In the region of whole periphery, the 4 beta electrical, the region of 4 beta electrical, the conductor which lies in the region of 4 beta electrical, they will only be responsible for demagnetization action, right? So now you can calculate. See here, first calculate the total MMF, magnetomotive force total, FAR total, due to AR suffix AR stands for armature reaction. Total armature MMF when you calculate, MMF due to armature reaction MMF, see it is nothing but product of number of turns, right, and the current. So number of turns it will always be taking per poles, right, and current is always taken per parallel path, right? We have discussed this when we were discussing the EMF equation, right? So MMF is nothing but turns into current, that you know from basics, right? So now N is the number of turns, I is the current in armature coils. So see this, I have taken this particular 1 turn coils, right? So this is a single turn coil. So single turn coil is basically having two turns, the two conductors, right? This single turn coils, it is having two conductors, right? See here, so this is forward conductor, current is like this, and this is return conductor, right? So this is a single turn coil in which you can only see a single turn, only one turn. So like that there are so many turns, right? There are multi-turn coils, right? Suppose if you want to draw multi-turn coil structure, then you can easily draw it. Multi-turn coil will be something like this. Multi-turn coil will be like this. So multi-turn means it will be having several turns, right? So in actual case it will be having so many turns, right? So this is a multi-turn coils, right? Here I have seen a 3 turns coils. There are 3 turns, 1 2 3, right? So this is a single turn coil. So that means single turn coil, it will always have two conductor, one forward conductor, one return conductor, right? So that means one turn means two conductors only, right? One turn means two conductor. So suppose the total number of conductors which are present in the machines are Z, capital Z, right? That is a standard notation for total number of conductors in machines, right? For DC machines, right? So here one turn is two conductor, right? One this conductor and one this conductor, forward conductor and return conductor, 1 plus 1 2. So one turn is having two conductor. Or you can see, or you can understand this, one turn means two conductor. That means one conductor is equal to 1 by 2 turns, half turn, right? Similarly, if I say there are total Z number of conductors, then how many turns? There will be Z by 2 turns, right? For example, if I say that if there are total 100 conductors in a DC machine, suppose if there are total 100 conductors, that means capital Z is 100. And you know that one turn is equal to two conductor. Then how many turns will be? There will be 50 turns, right? You understand now? So what is the total value of armature reaction? MMF, FAR total, F suffix AR suffix total, right? TOT stands for total. So N is the number of turns per pole. So number of turns, total number of turns you have calculated, it is Z by 2. Per pole you will always calculate per pole, that is advisable, right? So here always take number of turns per pole, so divide by P, and current I is armature current per parallel path. So if there are total 8 number of parallel paths, then in one parallel path the armature current will be IA by capital A, right? So this is the total armature reaction MMF, right? FAR total Z by 2 by P, right, into IA by A, right? Now if you want to calculate the demagnetization armature MMF, see this, if you want to calculate the demagnetization armature MMF, then I told you that how many armature conductor which are responsible for demagnetization action? 4 beta electrical, right? 4 beta electrical out of 360 degree region, right? So 4 beta electrical divided by 360, in this region the conductor which will fall in this region, they will only be responsible for demagnetization action, right? So just multiply this 4 beta electrical by 360 to this total armature reaction MMF. So Z by 2P into IA by A is as it is, and this is the multiply here by 4 beta electrical by 360 degree. So you will get FAR demagnetization, that is nothing but Z by 2P cancel divided by 2. So 4 beta electrical become 2 beta electrical and 360 become 180 into IA by A. So this is the number of turns per pole, that is Z by 2P, right? And this is the 2 beta electrical by 180 degree. This, in this region, the armature conductor which fall in this region, they will be responsible for demagnetization action, and IA by A is the total armature current, is the armature current per parallel path. So capital A is the total number of parallel paths. IA by A, I suffix A by capital A is the armature current per parallel path, right? Beta electrical is that angle by which you are shifting a brush, right? Z is the total number of conductor, P is the number of poles in the machine, right? So this is the calculation of demagnetization armature reaction MMF, right? Similarly, you can calculate the cross magnetization armature ampere turns, right. So once you have calculated the demagnetization armature ampere turns, and once you have calculated the total armature ampere turns, right, then can you calculate the cross magnetization armature ampere turns? It is very easy. Just subtract this demagnetization armature ampere turns, armature MMF, demagnetization, just subtract this demagnetization armature reaction MMF from this total armature reaction MMF, right? You will get your cross magnetization armature reaction MMF, see, right? So for all the conductor which lie in the remaining region, that means in this region and in this region, so this region conductor and this region conductor, they will be responsible for cross magnetization armature ampere turns, right? Cross magnetization means, recall that original figure of armature reaction. See, so this was the cross magnetization armature reaction flux, right, which is coming in this left direction for this cross and dot position, right? So this cross magnetization flux, this is phi AR cross, right? This is known as armature flux due to cross magnetization. This is written as phi AR cross magnetization, right? Phi AR cross magnetization, right? So we will now calculate the armature reaction MMF due to this cross magnetization action, right? You understand? So now you have understood what is the direction of armature reaction flux due to cross magnetization. It is like this, right? It is like this. It is like this, right? So now see, when you apply right hand thumb rule for all those conductors which are responsible for cross magnetization, so which conductor are responsible for cross magnetization? This conductor, that means the conductor which lie in this region and in this region. So these conductors are only responsible for cross magnetization, right? So how to calculate the armature reaction MMF due to cross magnetization? Just subtract this demagnetization armature reaction MMF from the total armature reaction MMF. You will get this armature reaction MMF due to cross magnetization action, right? So the same I'm going to do, right? So once you've calculated the armature reaction MMF due to demagnetization action, you can always calculate the armature reaction MMF due to cross magnetization action, right? So the remaining conductor will be responsible for cross magnetization effect of armature reaction, right? So now we are going to calculate the same, right? So simply you have to subtract, right? That means you simply have to subtract the demagnetization armature reaction MMF from total armature reaction MMF. So you will write here, FAR cross, that means armature reaction MMF due to cross magnetization action, it will be nothing but FAR total minus FAR demagnetization, right? So you understand the simplest logic. So from total armature reaction MMF, if you subtract the demagnetization armature reaction MMF, then you will get the armature reaction MMF due to cross magnetization. So what is the value of total armature reaction MMF? It is Z by 2P, right? It is Z by 2P into IA by A, right? And here what is demagnetization? Armature reaction MMF Z by 2P into IA by A, right? So in bracket you can write 1 minus 2 beta electrical, right? 2 beta electrical by 180 degree. Alright, so simply you have not 1 minus, sorry, this is in the bracket, this is 2 beta electrical by 180 degree. So when you take this whole term, common, then you will write 1 minus, right? So you write Z by 2P into, you take this term common, IA by A. When you take this common, so here it will become 1 and here it will become 2 beta electrical divided by 180 degree, right? So this is the armature reaction MMF due to cross magnetization action of armature MMF, right? So here you have now calculated FAR cross magnetization, right? Which is basically the armature reaction MMF due to cross magnetization action of armature reaction MMF, right? So this is the corresponding value, right? So this is the calculation of cross magnetization armature reaction MMF FAR cross, that is right, that you have calculated. So thank you very much. Thanks for watching. Please subscribe the channel. If you like, you can subscribe for all such kind of clarity and conceptual videos.